Okay, a quick look at the calendar. We are on our second class in terms of the financial math. Last time we introduced percentages and then simple interest. Today we'll talk about something more realistic than simple interest. That's called compound interest, where you get interest on previously earned interest. Then we have 2 more days of finances, 2 days on something called fractals, and then we're reviewing for the third exam. The financial project is officially not yet assigned, but I know that at least one person has made real good progress on it, so I'd encourage you, if you have time now, to not wait. Again, our third test is not a final exam, it's just a regular old test. Any questions on the schedule? Okay, then we'll start here at the top of page 9. Jeremy, number 1. Sure. Okay, thank you. Okay, Stephen. Okay, so $5,000 in the bank, but it's earning 6% interest every year. Okay, so there's a natural way to do this, and then there's a better way to do this. So the natural way to do this is to say, okay, we need 6% of 5,000. That's $300. So how much do you have at the end of 1 year? It's $5,300. And then you take 6% of what number? Of 5,300. Is that going to be more, less, or equal to the $300 interest you got in your first year? It's going to be a little bit more. You're going to get another $300, but then you're going to get interest on the first $300, right? So you might get like another $5 interest that second year. And it keeps going like that. So every year you're going to get a little bit more interest than you did before because you earn interest on interest. So that's the natural way to do it. The better way to do it is to think about this problem that we saw a few weeks back about rabbits. I'll just remind you. So the rabbit population starts at 1,000 and increases by 20% per year. You guys remember this problem? And so the natural way for us to do that was to say, okay, start with 1,000 rabbits, and then you add on another 20%, which is 200. So at the end of the first year, you have 1,200. And now we're going to take 20% of what number? Of 1,200. And that turned out to be 240. And so we added that to the 1,200. And that gave us 1,440. And then we took 20% of that, and we kept going. The easier way to do it was to say, wait a minute, if you increase by 20%, then what percentage do you really end up with when all is said and done? If you increase something by 20%, then what percentage is still there at the end? Is 120%, right? The 100% that you start with plus the 20% you gain. So we ended up saying, hey, wait a minute, here in blue, if we just do times 1.2, that's the quicker way to calculate the final amount at the end of each year. And repeatedly multiplying by 1.2, which is what this exponent does, was something that we called exponential growth. So gaining 20% a year, we just had to multiply the start by 1.2 over and over again. What's our magic multiplier in this problem? A 6% increase. It's 1.06. So let's see here. I guess we have year, and then we have the money at the end of that year. So at the end of year 1, 5,000 times 1.06. And what is this equal to? It's 5,300. Straight in one shot, instead of first finding $300 interest and then adding it to 5,000. This just gives it to us. And then in the next year, we're going to take what new number? 5,300 and multiply by 1.06, 106% of what you had. 56 what? 18. And then we can do this one more time. What's the new number? 5618 times 1.06. Let's write this one with all the decimals. Any questions on this idea of just keep multiplying by 106%? If this was simple interest, meaning you only get money on what you originally put in, then how much interest would we be getting every year? 300, just a straight 300 year after year. That's simple interest. This is compound interest. The first year you made 300, second year you made 318, third year you made, I don't know, 340, whatever it is. Okay, here's the quick way to do this. I want you guys with the calculator to type the following thing in. 5,000 times 1.06 to the third power. What did we get? What did we get? 59.55, right? Exactly that. So that's the quick way to do this, is to just say, okay, all you're doing is multiplying by 1.6 over and over again. That's an exponent. So then in our general form down here, 5,000 times 1.06 raised to the t, whatever t is, however many years you wait, just put that on the exponent. And that's how much money you'll have at the end of that year. Okay, so let's start filling in this table together here. In year 0, that's the start of the experiment. How much money did we have? 5,000, so we're going to put that there. Now we haven't yet found how much money we have at the end of year 10. Would you rather do this way in black or the blue?
The blue.
Why? That's right. If you want to get to the 10th year and you do the idea of the table here in black, you got to do the first 9 years in order to get the 10th number. But we'd rather just jump to the answer. So we're using blue here, 5,000 times 1.06 to the 10, then fill it in that spot. And with your neighbors, you can divvy up the work a little bit. Let's get this whole table filled in. And when you're done filling in the table, plot all of those points. So what we should see here, now I didn't even bother plotting any points, so mine is not going to be as exact as yours is, but we should see that it isn't a straight line that connects these things, right? It's something that grows, would you say it grows quickly or slowly in the beginning? Slowly in the beginning. Things are fairly flat, fairly steady growth here, but then it really starts to jump up quite dramatically towards the end. Right? And that's what happens when you have money invested and you get compound interest, is that in the beginning, okay, whether you get interest on the original 5,000 or on 5,300, we're talking another $18 in interest. It doesn't make that much of a difference in the short term. But at some point, you're down here. What was the number for 50? So 6% interest on 90,000 is quite a bit of money. And so going from year 50 to year 51, you're going to gain a lot of money, a lot more than you gained in your first year. And this is the benefit of compound interest. This is also the curse of compound interest. If you have your money in some kind of an investment, then you like this graph. But if you have your money tied up in a car loan or a house, like a mortgage, then this graph is working against you, right? So it's just two sides of the same coin, and you guys are probably on both sides in different facets of your life. All right, let's go on to the next page. Number 3, we're back to Sam. Okay, so what we ended up was this formula. That's what we used right there, 5,000 times 1.06 to the t. So we just got to change it. Instead of 5,000, what are we calling it in general? Is P for principal times. Now, why was it 1.06? Because it was 6%. So we're going to call it R. So how can I write something in there with an R in it? R, okay. Plus 1, right? I mean, that's what it was. It was 1 plus 0.06. That's why it was 1.06. Exactly, 100% plus interest. And then out here, it stays the same. It's just T. So that right there is our compound interest formula. And I just want to highlight this word right here, annual. That's if you get interest once a year, annual compounding. Okay, let's try number 4. Griffin? Okay, thank you. So let's give this one a shot. We are looking for the future value of $875. What's the value of P?
Oh,
875, that's what you invest. 1 plus, how much is R? 0.0675. Always make sure that you use R as a decimal. If problems involve percentages, it is almost certain that you're going to convert that to a decimal if you're using a formula. Okay, and how much is T?
7.5.
7.5 years. Okay, this is just a calculator problem now. How much? 13 cents. Okay, so that's how much money we have in 7.5 years. Questions on using the formula? Yes, Damien. Oh, was it exactly 13 cents or did we round? So the squiggly means not exact. Yeah, approximately. Okay, what was the goal? 2,000. We're a little bit shy of 2,000. Okay, so then it says how much more would you need to invest to meet the target? Is it just as simple as subtracting these two numbers? If we just invest another, what, $570, won't that get us there? It's not going to count the interest. If we invest another 570 in the beginning, we're going to end up with more than 2,000 at the end. Yeah, that's what we're going to do. We're using the same formula again, but what's the unknown is the P. Right, we're trying to find the P. How much is the F? It's 2,000. If you want 2,000 at the end, this is how you set it up. You say, okay, I want the future value to be 2,000. I don't know the principal. We'll leave it as P. Still 1 plus 0.0675. Still to the 7.5. Any questions on the setup there? All right, now this is no longer just a straight arithmetic problem. This is an algebra problem because the thing you're trying to find is buried, right? In the blue formula, the F was already by itself, so it was just straight arithmetic. But in the red formula, the P is buried. So we can solve this. Let's first get a number over here. So my calculator, folks, raise this thing to the 7.5. What do we get? $1.632. And then how do we solve that equation for P? We just divide by that number. Called what? Chad, what'd you get?
Oh, I got 12.5.
You said 12.25.38. Other votes? Okay?
Yeah, I just did mine. Oh, I got it.
Okay, so let's talk about this rounding idea. Okay, it's not that big a deal. We're off by what, 11 cents? Who cares? In the next problem, it's going to make a difference. So we need to be careful about rounding. When Brandon shared the 1.632, he rounded that number, right? He had more digits in his calculator. We don't feel like writing it all out, so it's okay to just write 1.632. But if you just retype and you type 1.632, you're changing the answer, and that's not so great. So let's show you how to do this a little bit better. I'm going to type in this thing in the parentheses, 1 plus 0.0675, and then raise that to the 7.5. So this will give us the number that we saw before, 1.632. But instead of retyping that, we can use that, and we can do the following. We needed 2,000 divided by 1.6. So 2,000 divided by. Now on this calculator, there's it's hard to see from where you are, but there's a yellow ANS here at the bottom, and that stands for answer. Second ANS. It's going to take 2,000 and divide it by the previous answer, and this will be the most exact answer that we can get. Turns out it's the 38 cents. So yeah, so that's how we do it on this calculator. Now on other calculators, you're probably going to find the ANS key elsewhere. Well, here on I know several people have a calculator like this. It's in the same spot as it is up there. It says ANS is right above the minus sign at the bottom row. So make sure that you know how to use that answer button, because we need it in the next few problems. Okay, so we're going to cross this off, and we're going to say don't round. Okay, so let's go on to number 5. Casey. Okay, first I'm going to cross off the sentence about the half year. Your book does something that I'm not a fan of. It talks about, like in this CD business, that if you invest for 7.5 years and it's an annual thing, then you're only going to get credit for 7 years. And I don't know of any place that works like that. And if you need to take your money out in 7.5 years, then you certainly wouldn't put it into something that cut you off at 7 years and didn't let you gain any interest in the last half a year. So, so I'm crossing that off because we ignored that in the previous problem. Okay, so here's the idea. Instead of giving you interest at the end of each year, they're going to give you interest at the end of each month. Now, they're not going to give you 6.75 every month. That would be crazy. They're just going to give you the right fraction of 6.75. What fractional part of 6.75 will they give you every month? They'll give you 1/12. Okay, so it's no problem. So you're still going to have 6.75%, just, it'll be spread out over the course of the year instead of in one lump sum at the end. Now, do you guys have a sense? Is it better or worse for you to get a little bit of interest every month than all of your interest at the end of the year? You're going to gain a little bit of interest every month.
But in the end, you're going to get the more money every month.
That's right. If you let the interest grow every month, then, okay, in your first month, let's see, do we have this number? I guess we don't. So in your first month, I don't know how much interest you get, let's say $20. And so if you get interest just once every year, then you're just going to get like $20 a month. You'll just get it all in one shot at the end of the year. 240 bucks is what you'll have. But if you get $20 in the first month, that is now something that you get interest on. And so maybe in the second month, you get like $22. Not just the same $20 again, but interest on the first $20 that you earned. But if you get one lump sum at the end of the year, you don't get that interest built up every month, right? So this is going to be better for us as investors. So here's what we do. Well, we only have this one formula. So here we have to modify it a little bit. It's not fair to just change to make R 6.75. What do we have to do to really find how much interest you get every month? We're going to divide that by 12. Okay, let's do that. Okay, so I'm going to use that same formula, still starting with P, which is what, 875? 1 plus, okay, so 0.0675, but we cut it into 12 equal pieces. And there's one more modification we need to make. If I just put 7.5 up there, then that's 7.5 years. But we're now talking months. What do I need to do to 7.5 to make it a monthly figure? That's the right idea. We're going to add 6 at the very end. We're just going to take that 7.5 years and multiply it by what number? Number of months, 12. Just multiply 7.5 by 12, and that's what we're going to put up here. Yeah, so what is it? 90. Yeah. So instead of looking at this formula as telling you what you have at the end of each year, we're just tweaking it so it tells us what we have at the end of each month. So we tweak the interest rate to make it a monthly figure, and we tweak the time to make that a monthly figure. So you can just type this in all in one shot, but it's a little bit risky to do so. So I'll encourage you to actually just do that multiplication separately. Just do the 12 times 7.5 separate, put one number up there, and then type this in one shot. If you do the number in the parentheses, what's that? Made a mistake, thank you. If you type in the number in the parentheses, there's a good chance you're going to have some rounding errors because that number is going to be kind of messy. So I'm going to leave that and just ask you to type this in one shot. And I'll say be very careful because if you type it in as it sits up here, you need to make sure you put extra parentheses around up there, and that's really easy to forget to do. That's why I encourage people to just find that as a single number. Okay, so some calculator folks, what do we get? 1449.62. Anybody confirm or get something different? Confirmed. How much more did we earn? You guys still have this number, right? Doing it annually, we were at 1,225. Doing it monthly, we're at 1449, about $225. Yeah. Alicia's first comment was that it's not that much more. Relative to the $1,200, an extra $200 is pretty significant, isn't it? You know, I mean, it's like 18% more, right? Just relative to the starting number. Okay, can you guys do this next part right here? What if we compound daily? So you got to change two numbers in my formula. What two numbers get changed? Still 7.5 years. Don't worry about leap years, but it's a good question. That's a good question. So what two numbers change in my problem? The 12 changes, and yeah, the 90 changes, but that's only changing because of the other 12. It's really the two 12s are changing. Okay. What are they changing to? 365. Yes. Yeah, both of those 12s are going to change to 365s. Can somebody do this 7.5 times 365 number for me? Okay. That means something in the context of this problem. What is this 2700 number counting? That's how many days in 7.5 years. That's all. So we're just using the same exact formula over and over again. It was originally a formula for years. We're just modifying it so we can use it on a daily basis. What about half a day? That means you went into the bank in the middle of the afternoon and picked it up. I don't know. Well, it's all approximations of reality anyway. Okay, what's the final number? Okay, how much more did we make there compared to monthly? $2. Okay, that's fairly insignificant actually, and maybe surprising. We made a lot more going from yearly to monthly, right? We made like an extra $200 and change. But then going from monthly to daily, we only made about another $2, which isn't all that much. Okay, let's go on to 7, and I think we're over to Evan. Okay, that's the formula that we essentially figured out. I will compare it to the one from all the way at the top of this page. This was our annual compounding formula. Remember I highlighted the word annual? You can only use it if it's annual. But if it's monthly or daily, you can't use it. You got to use this guy. But all we did was change the interest rate to an R divided by N. N is how many times you get interest per year. Compounded N times per year. If we were doing this monthly, what was N? It was 12. If we were doing this daily, what was N? 365. So all you got to do is know, for example, daily means N is 365. Right? That's all you have to know. Okay, so there's the formula that we figured out. Let's move on to the next page. And you guys have 3 problems you're going to work on with your neighbors here. You're going to carefully use that formula to write out, and then you're going to carefully use your calculator. And you are also going to be careful not to do any rounding, because rounding here could make a significant impact on the end game. We were only talking about $2 before, so be really careful not to round anything. Okay, so what we should see is that we're getting essentially the same number, and really the differences are in the pennies or even less than pennies. Now I've written the answers here from somebody in the class, and something strikes me as funny. Going from every hour to every minute, the amount of money we have should be a little bit bigger, but at the moment it's a little bit smaller. So there's some like little rounding thing happening in here. But the point is that, and I think Griffin, do you remember that phrase that you used about what's happening to the money? Yeah, it levels off. Like the amount of money that we're going to get at the end of 7.5 years is leveling off. It's not just going to grow forever, and if we just get interest often enough, we'll have $1 million in 7.5 years. It won't happen. We're pretty much at our cap. It's 1,451 and like 68 cents. Like that's like we're not going to get above that no matter how often we compound interest. So that's what it says here in 11. I think we'll go to Brandon. Okay, so continuous compounding is our new phrase, and what that means is you get interest all the time, every moment of every day, not just once at the end of the month, which is what it looks like on your bank statement, not just once at the end of a day, not just once every hour, not just once every second, but every moment in time, you're getting like a little fraction of a penny thrown at you, and it just accumulates in this pile, right? And so continuous compounding just means all the time, an infinite number of compoundings every year. And here's our formula. F equals P e to the RT. All right, now part of this kind of looks similar. So I'm going to cross this thing off here, this e to the r, and just remind you that the formula that we saw before was this. And if I cross off the stuff in here, I see p down below. I see t as an exponent. So it does have some things in common with the formula we just used. But somehow this stuff in here translates into another letter, E. And all of a sudden the interest rate is up there in the power. It wasn't before. And what letter did we lose? We lost N. Okay, well, how many, n is the number of times you compound every year. How much is n in this continuous case?
E. Oh.
N is infinity, right? If we're saying continuous compounding, then n is infinite. So no formula I give you can have n in it because you can't plug infinity into some formula and hope to get some magical answer at the end. So maybe I'm not surprised that the n went away, but then there's this new e, which I don't know what's going on. It feels like it's just another variable, but it's not. E is a fixed number. What's the most famous mathematical number where we just have a letter associated to it? Is pi, right? Right? Pi is 3.14 and change. It's a number, but we give it a letter because it's really important. E is that kind of a thing. It's a number. It's just like phi, our golden ratio, right? 1.618 and change. E is another magical number that's important enough to warrant a name. It's E. All right, so E, according to this thing here, is approximately 2.71828. Your calculator knows what E is. Let's do this. It does. So for me, on this calculator, I see the E right here above the division symbol. I'm looking for a lowercase e, not a capital E. So if I do second and then that yellow button right there, I will get that. If you have only an e to the x button on your calculator, here's what you do. You find your e to the x button. For me, it's over here. Second, this thing, and then type a 1. So I want it to tell me what e to the 1 is. And it's just going to be e.
Okay.
Right? So your calculator knows what e is. Is there anybody who cannot find e on the calculator? Should tell you 2.7 and change. Where is the button?
You tested it out in the beginning of the year and said it would work.
Man. Calling me out on my guarantee. I'm going to come back and look at it in a little bit. Okay. Anybody else having trouble finding the e? 2.7 and change?
So I have the e to the x.
Yes.
When I press it, it's
Good. So you're clear. Hit the clear button. Type in the 1 first for the power, then press that button.
oh,
Okay. Some calculators you got to type the power and then the e button. Okay. Yeah. Okay. So it turns out that if you do this thing continuous compounding, that's the formula that you get to use. In some sense, it's the simplest formula of all the ones that we've looked at today. All right, let's go on to the next line. Here it just says the derivation of the formula and the magical appearance of that number e requires calculus. We're just going to take it on faith. And we'll try number 12. I think we're back to Mary. Okay, so there are two really important words in this question. One of them is compounded. What's the other one? Continuously. Those are the two important words. If I said compounded monthly, then you got to use the formula with the n. That's the one that we just used half a dozen times. But if I say compounded continuously, that word, continuously, and only that word, that's your cue that we're using this formula, okay? The only time we use this formula is if you see the word continuous, no other time. Okay, so F equals, how much is P? Still 875. E is just E, you just put it. You don't replace it with a number, it is a number. What is R? 0.0675 times 7.5. So this is what we type. I will do it on my calculator here. You can just do the whole thing in one shot, but be careful. That power needs to be in parentheses. On many calculators, it's automatic. So it should look something like that. Again, the power needs to be in parentheses, but it probably is if you're using a button on your calculator.
I have a question.
Yeah.
So, do I have to do this first?
No, you need to not do it as e to the 1. You need to do it as an e to the x. Yeah, use that green button right
But
there.
I don't put a 1 there?
No, don't put a 1. Okay, what do we get? 1451.6757. All right, that is your limiting value. If you compound interest like 1 trillion times a second, it will be like a sliver of a penny less than that number. That's the magical number. That's the extreme. Okay, can't be any more than that. So this is about 1451.675791. Questions on that? In a couple of minutes, I'm going to come around, and if you weren't able to get this on your calculator, I want to make sure that you can, because you'll need to be able to do it for our test, but we'll come back to that. All right, let's see. We'll go on to 13, Ed. Okay, we'll move on to 14, Lila. Okay, so here's the idea. The bank is going to advertise two different rates. And if you go to a bank, you'll see on the wall some bulletin board or something. It'll have a column that says APR and another column says APY. And the two numbers will be pretty close to each other, but they're different. APR, like if I said 6.75%, that's an APR. But if I say 6.75% annually versus 6.75% monthly, that's different, right? They're different. Even though it's the same 6.75, it's different because I'm compounding a different number of times per year. And so this whole business of APY is like, hey, forget about whether it's monthly or daily or whatever. Just give me like the net result. Like, what am I really going to end up with at the end of the year? That's what this APY number is. So on the face, it could be 6.75, but maybe it really is something like 6.8 if you just wait until the end of the year and you get all the money in one shot. That's what we're after here. So let's try this example that Lila read. $1,000. At the end of the year, we get $1,099.60. I don't care how you got there, but we're now going to figure out, all right, what did you really make on your money? Okay, so we want the APY. It's a formula that we wrote recently. We'll just write it again here. Oh, you know what? We're not. We're going to use the formula that we started with today. F equals P times 1 plus R to the T. How often is interest compounded if we're using this formula? Once a year. This was our annual formula. Everything else was based off of this one. And once a year is what we want to do. So let's give it a shot. F, what number is F in this problem? 1,099.60. What is P? 1,000. 1 plus. What is R? We don't know. R is what we're after. R is the interest rate that we're trying to figure out. What did we really earn? What is T? It's 1 because we're trying to find out what's it worth in a year. It's 1 year past. So that's just a 1. So that's the equation we need to solve. And I will highlight that the APY is the R in this formula. So this is just 1,000 times 1 plus R. Some of you may feel obligated to distribute that 1,000. Don't. How can I move the 1,000 out of the way? Divide by it. So let's divide both sides by 1,000. Uh, 1099.6 over 1,000 is okay, and then the 1,000 disappeared on the right-hand side. And then finally, to solve for R, what do we do? Subtract 1. And what is that as a percentage? Good. That's what you made, 9.96%, which is quite good in this economy. I think my bank is paying me 0.1%. Oh, the joke's on them. There's like hardly anything in there. So there you go. Okay, questions on this one? So we used our annual formula because it was an annual question, right? So if you're going to try to find APY, use that formula right there. The value of T is always going to be 1. It's an annual thing you're trying to find. All right, let's go to 15. Jake? Okay, give that one a shot with your neighbors.
Well, if you rounded it, it'd be
6, 8. Okay, any questions on this? Whoops, any questions on this one here? About 11.68%. Okay. So on the face, they might have said 11%, but we're going to compound it monthly. In reality, what that means to you, your bottom line is 11.68% at the end of the year. That's the APY, right? It's what's really going on. Okay, next page. 16. Who's our reader now? Aileen. Okay, so you have 3 choices. Your bank is offering each of these things. You're going to decide which one you want. You can do a 6.7% compounded continuously, 6.75% compounded monthly, or 6.8% compounded quarterly. How much is N in the last example? If we say quarterly, then N is 4. It's how many times per year you get interest, right? 4 times. It would be every 3 months, but it's 4 total times. Okay, you have 3 problems to do, and your job is to figure out which one is the best.